Nani.
Hello?
All right. Hello? All right. Uninhibited, inhibited growth and decay. So it's either going to grow or it's going to die off.
Ungrow.
Okay, yeah, ungrow. Ungrow.
The opposite of grow.
I know, right? Okay. Newton's law of cooling. So that's important.
Cool.
If we if we get another like H of potato, you'll be like, oh, okay. All right. Solve differential equation involving uninhibited growth and decay. All right. Situations in science, nature, economics, such as radioactive decay, population growth, and interest paid on investment in which quantities A varies at time t in such a way that the change of A with respect to t is proportional to itself. These situations can be modeled by the differential equation dA dt is equal to k of A. There's some math for it. K is going to be the rate. Oh, is that more basic? Okay, if k is greater than 0, then the rate of change A respect to is positive, so therefore it's going to be a growth. If k is less than 0, it is going to be a decay. It's decreasing. Suppose that the initial amount A sub naught is substance is known, giving us the boundary condition or initial condition. So A is equal to A of 0, so initial, or A sub naught when t is equal to 0. So I don't know. I always refer to it as A sub naught because I don't know. That's the way I was taught. So if you hear it differently, just your initial or A sub naught, because there's like a sub.
Yeah.
It's like below A sub O, or
You started
A sub
calling it that, and I
A sub
started
0,
calling it that.
A sub naught. Okay. Anyway, all right. We solved differential equations in the form dA dt equals k of A by writing that as dA over A is equal to k dt. So a little bit of algebra, you could actually get that, right?
Yeah.
A little bit of algebra. This right here changes to this right here, right? Yeah? Okay, good. All right. Integrate both sides of the equation on the left with respect to A and on the right with respect to T. So this is actually the work for it. When I taught this last year, I was trying to go through and like explain how to actually get all this. Just go down to here. A sub naught is my initial. A is my end result. E to the kt, it's the rate times time. K is the rate. T is the time. Is that easier? Yeah, just go by that. Let's do that. So right here, this is going to be k is greater than 0, so it's going to be a growth, and k is less than 0 for a decay.
Yeah.
Okay, assume colony of bacteria grows at a rate proportional to the number of bacteria present if the number of bacteria doubles in 5 hours. So, what does that mean? Start off with that information. Okay, so it's it doubles, but so what is so t is going to be 5, right? So yes.
Yes.
Okay, good. So t equals 5, but if the number of bacteria doubles, what does that give me? I don't have a number, right? There's no actual like 4. Okay. However many there is going to double. So what could I actually say given that information? I want you guys to think about this because on all these problems you have to think about, conceptualize, and talk it out. Talk it out. What about the initial?
Yeah.
Times 2, there we go.
Yeah.
So it's going to be 2a sub naught equals, whatever, something. So whatever my end result is supposed to be 2 times my initial. Okay, how long would it take for the number of bacteria to triple? Okay, let's go with the information that we have. Okay, so let's say that I'm going to have 2a sub naught is going to be a sub naught e to the k, but what's my t?
5.
Okay. So what can I do from here? Okay, try to find for k. So what would I do to both sides here? Okay, let's divide by a sub naught. Come on. So that's going to give me 2 is equal to e to the k, 5k, right? ln, right? So ln, so it's going to be ln 2 is equal to 5k. Divide by 5, right? K is equal to ln 2 over 5. That's important there. Okay, so now, given that information, so now I know what K is. K is always going to be that. Given this, it's always going to be. So now I can actually find other values from this. So what's the other value I'm looking for?
Or the triple.
Triple, right? When's it going to triple? So how would I write that out?
So 3 times a sub naught.
Okay, very good. So 3a sub naught is equal to?
How long would it take? Is it a sub naught e?
A sub naught e to the
ln 2 over 5.
ln 2 over 5
And then we're trying to find the time times 5.
times t.
T, right.
Yeah.
We don't know the time. And then could we do the same thing that we did on the other side, just divide by a sub naught to try to find the t?
Yeah. So you can get what?
So then 3 equals e to the natural log 2 over 5. You didn't get any sleep. And then natural log it. I'm still dying.
Okay, so ln.
Yeah, natural log it.
Okay. And so it's going to be 5 ln 3 over ln 2 is equal to t.
No. Do we plug that back in to find the...
That's my favorite time.
That's your favorite time? Okay.
I'll end for you.
So let's see what we get.
How many hours of sleep I get?
And is there asymptote right there at 0?
Always approaching, never touches.
Always approaching 0 but never touching 0.
Just to get it wrong. Because maybe you did one of them.
I could just...
Or you just do it. Only that's not how much sleep is then.
So what do we get?
A number.
Y'all got calculators. Come on now.
You right.
What are you smoking? Seriously.
What?
Seriously, you got the dark shades on in a very dark room in the middle of winter when it's the darkest at this time of the morning.
It's also cloudy. Yeah, it's also
And
white
it's cloudy.
overcast.
Really like the shade. I really don't.
7.92.
So let's say it's going to be about.
At this calculator, check out right out.
So we can say this is going to be about what? 8.
Still feels higher.
It's about 8 hours, right?
Yeah.
So this is a growth. So it didn't. It took to double. It took 5 hours. To triple, it took 8 hours. Okay, so important. Anyway, are we good here, or did I lose everyone?
No, I understand it.
Now let's see how long it would take to quadruple.
Ooh.
Oh
You can do that on your own time.
Oh no. You just change the 3.
Okay. For a radioactive substance, the rate of decay is proportional to the amount of substance present at time given t. That is, if A is equal to A of t represents the amount of radioactive substance at time t, then when k is less than 0, okay, so that means it's going to be a decay, right? Okay, half-life. Depends on radioactive substance. The half-life of radioactive substance is the time required for half of the substance to decay. So we know that given the initial amount, the half-life means how much is left. Half of it, right? There's going to be half of it left. That's important. It's half of my initial quantity. That's what's going to be left, right?
Mm-hmm.
Given whatever, type of substance it is, it's going to have different rates. So there is certain, I was watching like CSI a while back. Anyway, and they actually have for like chemotherapy and stuff for like brain tumors and trying to get rid of brain cancer. So they actually have radioactive substance that has a half-life of 1 day. So in 1 day, it actually decreases by half. And from there, it actually keeps going, eventually approaching 0. But, it is, I didn't even know what it was. Some weird isotope. All right, skull of an animal found in archaeological dig contains about 20% of the original amount of carbon-14. Okay, carbon-14 is a radioactive substance. Okay, so the half-life of carbon-14 is 5,730 years. How long ago did the animal die?
Oh my gosh. Okay.
Okay.
It doesn't matter.
Settle our problem.
Okay,
Numbers we got.
stop to think about what you have.
We have one of our T's.
Okay, I know.
Oh man.
No, seriously, I know. What do you know given this problem? Half-life. Very good. So the initial amount would be half, right?
Yeah.
Would be half.
So 1/2.
So
A
so
sub
I'm going to what? Say it.
1/2 A sub naught. Or.
Oh, okay. So let's go back to the previous problem. Let's talk about the previous problem. So every time on that previous problem, I just kept dividing it out, right?
Yeah.
I don't know the initial quantity, but I keep dividing that out of the initial.
So then it'd be 1/2 is equal.
So
to
over here, my end result came out to be 3 times as much, right? Or 2 times as much as I did my math, right?
Mhm.
2 times. So it's twice whatever it is. So given a half-life, what should it be equal to?
half of it.
1/2.
Yeah.
The quantity will be 1/2. Whatever my initial amount is, I know it's got to be 1/2. So let's say if it's starting off with, over here my initial is 10, my half would be 5, right? And when I divide my 10, right? 10, so it's 5 over 10, still gives me 1/2. Every single time my fraction is going to come out to be 1/2. Okay, that's important, setting this up. 1/2 is equal to, okay, because I already took out the a sub naught. I took out that part, and so it's going to be e to the
5,730K.
Yeah, 5,730K.
really? Nope. Nope. Yeah. Nope. That's not right. There's 20% left. Okay. So the half-life is that. So if it's 20% is going to be there. So I know that whatever the amount is, it's going to be, so it's going to be 20%. So that's going to be how much? 0.2 times my a sub naught. That's how much is going to be left. Right? So this is important here because we know it's going to come out to be 1/2 always. So but given that, that's my half-life part. So now let's take a look at the next thing. So if the half-life is this, so that means when it's equal to 1/2, it's going to be this many years. Yeah, am I killing everyone? What are we trying to solve for here? Okay, so let's start off with, I know that when time equals 0, how much is there? 100%, right? When time equals 0, I get 100%. So it's whatever it is, I'm going to have my a sub naught, right? So I get time and I get the amount, and it's all 100% there. And so when time is equal to something, time is equal to something is 20% of that. So I get this. I get 0.2 a sub naught. So I'm looking for that. I'm looking for that information. So now I have to find the rate in which this actually works out. So given this information that the half-life is going to come out to here, I'm going to have to find this. So given this right here,
So you're going to plug in for K, not T? Or,
no, because I know what my initial is, right? I got to find for K.
okay, yeah.
That's what I'm trying to do here. So given this, I'm going to have ln of 1/2, right, is equal to K of T. All right, so what would I do here? So what is my T here? What is the T here now?
5,730.
There we go, yes. All right, so I'm going to change that. Divide both sides. So I'm going to end up getting K is equal to this nasty thing right here. So I have the rate. I just realized, is that what you were trying to say earlier before I got to the 1/2 part?
Yes.
Oh.
Isn't that what we were doing?
Yeah, we were, but I was trying to get on to the 0.2 part, like the amount of, so anyway, I was like, oh, like I was on like a totally different path. I'm like, no, get this. Okay, yeah.
Close
So.
number to 0.
Okay.
-0.0000.
All right, so I'm just gonna shelf that number over there. I'm gonna shelf that number. So I'm gonna say that K is equal to ln of 1/2, right, over. So if I break up that ln 1/2, it's a division, right? So what happens if it's a division? isn't it ln of 1 minus ln of 2? Say yes.
Yes.
Thank you. Yes, say. Okay, what's ln 1?
0.
0. So I could replace this with minus ln 2, right?
Mhm.
Okay, I can't. So I think I will. Because I feel like it. There we go. So I shelf that right there. Okay, so now that's some important information. I have a K. I want to know when T is equal to 20%. So I know it's going to be 0.2, right? Is A sub naught equals A sub naught e to the, I'm going to do all that, negative ln 2 over 5,730 times t. Okay, what's going to happen to those a sub naughts? Go away. So, I'm going to end up with what? Same steps every time. So it's going to be 0.2, right?
Yep.
Equals e to the negative ln 2 over 5,730 times t. And it's going to be ln of 0.2 negative ln 2 over 5,730. So from here, this is a nice calculator area. So we should get t is equal to, what's that? It's a multiplication, so it should be 5,730 ln of 0.2 over negative ln of 2.
You can switch natural log of 0.2 to negative natural log of 5, and then you can get rid of the negatives.
Okay. Or you can just plug it all in the calculator, it'll do it for you.
Oh, jeez.
How old is that creature? Or the skull?
Pretty
Is it older than Raiko?
Yes, it is slightly older than Raiko.
But they were still buddies in high school.
I know, right? Alright, so what do we get?
I guess I got 13,305 if you round up. But
Yeah. 304.64.
Wow.
yeah, 640.
There we go. 13,305 years, right? Yeah.
That's a pretty old beast.
Yes.
Beast.
It's not bad, right? So it's
Well, just a skull.
yeah.
How many penguins do you think that
Huh?
ate if it were like a saber-tooth tiger?
Like, could it eat
11,000 BC.
Okay. So, uninhabited growth decay, amount of years grows without bound or decays to 0. Base upper value m, that the amount y cannot exceed inhibited growth, or there's a lower value m that y cannot go below inhibited decay. For inhibited growth and decay models, the rate of change for respect to t satisfies a different differential equation. Now, what this means that there is it's another asymptote, but it's going to be a horizontal asymptote. So if you guys talk about like population growth, so let's say for instance we have population of rabbits in this area, okay? So just like, I don't know, off of the desert somewhere over there. Okay, so if there is no population control, they will keep growing until what?
Exponential growth.
Reach carrying capacity.
Yeah, they reach the
Carrying capacity. Thank you. That's the word we're looking for. Carrying capacity. That means that there is not enough space or there is not enough food for the environment for them. So it is going to be up to a certain point, and that's going to be the horizontal asymptote on a graph where it would not be able to exceed that. The population cannot exceed, kind of like the, they talk about by like world population. Our world population, they say that we've already exceeded the population of our natural resources here on Earth.
Rabbits.
Okay, but that's
That sounds like the greatest.
I don't know. There's like a Dan Brown book about it. All right. Anyway, inhibited growth model. Okay, inhibited growth. So that means the growth is going to stop somewhere, right? Okay, good. All right. So this is the model here. Okay, where k greater than 0 and m greater than 0 constants. Since k is greater than 0 and y is less than m, okay, increasing, guaranteed amount will never be greater than m, since this is going to be, the second derivative is going to be less than 0, so the graph will be concave down. Okay, so, and decay, same information, but this time the y is going to be greater than m, so it's going to be m. What is going to be, if it's a decay, what's going to end up having? So it's going to end up eventually going to 0, right?
Yeah.
Somewhere close to 0.
No.
Okay, so here's the graph. M is my horizontal asymptote, my carrying capacity. And right here, M is going to be the lower bound that we have for this. So a lot of times that's just going to be 0 in between there. Application Newton's law of cooling. This is H of potato. All right, so K, U of T minus T. Okay. All right. That states the rate of change of the temperature of the object with respect to time is continuous and proportional to the difference between the temperature of the object and the ambient temperature. What does ambient temperature mean? Of the room, right? Of the room where it's at. Okay, good. All right, that is, if U is equal to U of T is the temperature of the object at time T, and T is the constant ambient temperature, Newton's cooling law is modeled by the differential equation. So, let's see. So, it comes out to be all of this information right here.
All of that just for that?
That's the work for it. So you guys could actually see where it's going to be. Okay, yes, it comes out to that. Where U sub naught is the so let's see. Object is heated to 90 degrees. So what am I writing out first? Let's write out this right here. So it's going to be U of T is equal to,
The quantity of U sub naught
okay, quantity
Minus big T.
times
keep going the wrong way. E to the KT plus T. All right. So we got to go through and find some rates here. So object is going to be heated to 90 degrees. What do you think that should be? What do you think that is? Which one of these nasty, weird thingies that is written here am I going to replace it with?
T, the T, big T.
Oh, that's it.
Oh, U of T. Oh, initial U sub naught.
Yeah.
Is that what I heard? U sub naught. Okay. So it's going to be, what is T?
Ambient temperature.
The temperature around it.
Ambient temperature T. Ambient temperature T. What is the ambient temperature?
20 degrees Celsius.
Ambient temperature?
I know, isn't that a little chilly? I'm an Arizona boy, sorry. I know. Phoenix.
Okay. And what is this all going to be equal to here? After 10 minutes,
60, right?
is 60. Okay, so this is going to be 60 over here. And what else do I have for that 10?
Yeah, the T's could be, right?
Yep, there's my T. This one right here. Ah, wrong one. There we go. So let me see. Do some quick math. 40 equals 70 e to the k t, k10, sorry, or 10k. So 4 over 7 is equal to e to the 10k, right?
Yeah.
ln of 4 over 7 is equal to
E to the
10,
10K.
10k. So it's going to be 1 over 10 ln 4 over 7 is equal to k. So that's my rate, isn't it?
Yeah.
Okay, now I have the k. And now what would be the temperature after 20 minutes?
Alright, now we,
So I'm going to put the little t to 20, right?
yeah.
Okay, so let's see. I need your guys' help on this one.
Yeah.
So it's going to be u of 20 is equal to 90 minus 20 e to the 20, whatever my k is, right? I know what the k is.
Yeah.
So I'm going to abbreviate it here and plus 20. So yeah, put in that nasty k. So u of So what do we get?
42.857.
42.857?
Yes.
Okay. So u of 20, 42.857 degrees Celsius. Okay? Make sense? Like and subscribe.